Our planet floats in the vast, silent emptiness of space. It is a world teeming with life, a vibrant blue marble against the infinite black. From this distance, Earth appears tranquil, almost fragile, yet it is surrounded by an unseen force. A powerful, invisible shield protects us from the harsh realities of the cosmos. This force field is generated deep within our world. It extends far out into space, a silent guardian against a constant barrage of cosmic radiation, charged particles streaming from our own sun. This phenomenon is known as geomagnetism. This magnetic field is not something we can see or touch. Its existence is written in the ancient rocks of our world's crust. It guides the simple needle of a compass. The field is a dynamic, complex system. It is born from the violent, churning heart of our planet. Understanding this field means embarking on a journey from the deepest layers of Earth's core to the outermost reaches of our atmosphere, where it meets the solar wind in a spectacular, unending dance. The story of geomagnetism is a story of discovery. Ancient mariners who first trusted a lodestone to guide their way. Modern scientists launching satellites to measure its subtle fluctuations. This invisible shield is not static. It constantly shifts and changes. Its strength waxes and wanes over geological time. Its poles have even flipped, reversing their positions many times. The evidence for these dramatic events is locked away in the geological record. These changes have profound implications for our technologies and for the very evolution of life itself on our planet. In this journey, we will explore the very source of this planetary power. We will travel deep into the Earth, past the crust, past the mantle, to the fiery liquid heart of our world. Here, in a realm of unimaginable pressure and temperature, a colossal engine generates the magnetic field that defines our home. We will uncover how this geodynamo works, transforming the kinetic energy of molten metal into a vast magnetic bubble. This exploration will reveal not just a scientific curiosity, but a fundamental aspect of what makes Earth a living, habitable planet. It is a force that is integral to our existence, a quiet protector we rarely acknowledge. At its most fundamental level, our planet behaves like a giant bar magnet. Imagine a colossal magnet lodged within the Earth, aligned roughly with the planet's axis of rotation. This simple analogy is the starting point for understanding our world's magnetic behavior. This conceptual magnet has a north pole and a south pole. These are the points where the magnetic field lines emerge from the planet and loop back around. It is this property that makes a compass needle, a tiny magnet, align with Earth's field, pointing toward the magnetic north. This has been a cornerstone of human exploration. However, reality is far more complex than a solid bar magnet. There is no giant magnet at Earth's center. The core is incredibly hot, too hot for permanent magnetism. The source of our planet's magnetism is something much more dynamic. It is born of motion, heat, and the unique composition of Earth's deep interior. The field is generated by the constant flow of liquid iron and nickel in the outer core, the geodynamo, an immense, self-sustaining electrical generator at our world's heart. The internal engine creates a field that is not perfectly uniform. The magnetic poles do not align with the geographic poles. The magnetic North Pole is in the Arctic Ocean and is constantly wandering. The difference between true north and magnetic north is declination, crucial for navigators. Field strength varies, strongest near the poles, weakest near the equator. These clues point to a fluid, ever-changing origin deep inside Earth. Understanding this planetary magnet is crucial. The magnetic field does more than point compasses. It acts as a barrier, deflecting charged particles of the solar wind. Without it, the solar wind would strip our atmosphere, leaving Earth sterile like Mars. The field funnels particles toward the poles, where they make the auroras, a beautiful, stark reminder of the invisible battle above our heads, a battle our planet's magnetic heart has been winning for eons. The story of our relationship with Earth's magnetism begins not with complex equations or satellites, but with a simple, mysterious rock. For centuries, perhaps even millennia, people in different parts of the world discovered a peculiar type of iron ore. This dark, unassuming stone, lodestone, possessed an uncanny ability. It could attract small pieces of iron, seemingly by magic. The ancient Greeks documented this, Thales of Miletus, 6th century BCE. They called it magnetite, after Magnesia in Anatolia, humanity's first tangible encounter with magnetism. If a lodestone was suspended so it could turn freely, it would align itself, pointing north and south. The consistency was a profound revelation. The stone seemed in communication with a larger, unseen force. First practical use. China, Han Dynasty, around the 2nd century BCE. Early compasses were not for navigation at sea. They were used for divination. They were used for feng shui, to orient buildings and objects with cosmic energies. By the 11th or 12th century, Chinese sailors used magnetized needles floating in bowls. These guided ships across the open ocean. The technology spread along the Silk Road and via maritime trade routes, reaching Europe and the Arab world. Mariners could now determine direction even when the sun or the stars were obscured by clouds. This confidence launched the age of discovery, changing the map of the world. The early compass, simple device, enormous implications, a direct link to an invisible global force. Sailors and thinkers were mystified. What power reached across the globe to guide a sliver of metal? Why did it always point north? Some imagined a giant magnetic mountain at the North Pole pulling the needle toward it. Others imagined the pole star as a magnet, exerting its influence from the heavens. These early incorrect ideas began a centuries-long scientific quest to understand Earth's magnetism, a journey that would take centuries to unfold. As sailors ventured further across the globe, they began to notice subtle but important inconsistencies in their compass readings. The needle did not always point to true geographic north, the point defined by the Earth's rotational axis. This angular difference between magnetic north and true north, which we now call magnetic declination, varied depending on one's location on the planet. For navigators, this was not a mere curiosity, but a critical problem that could lead a ship disastrously off course. The need to understand and predict this variation became a major scientific and commercial driver. Navigators began the painstaking process of creating charts that mapped out the declination at different points across the oceans. By the 16th century, it was becoming clear that the field was more complex than anyone had previously imagined. In 1544, the German instrument maker, Georg Hartmann, made another crucial observation while studying a compass in Rome. He noticed that a perfectly balanced magnetic needle, when allowed to pivot vertically, would dip downwards, pointing into the Earth. This angle of dip, now known as magnetic inclination, also changed with latitude. It was nearly zero at the equator, meaning the needle stayed horizontal, but increased as one traveled towards the poles, where the needle would point almost straight down. These two phenomena, declination and inclination, provided compelling evidence that the source of Earth's magnetism was not some distant star or a mountain on the surface. The way the inclination angle changed systematically from the equator to the poles strongly suggested a dipolar source, similar to a simple bar magnet located deep inside the Earth. The global pattern of declination, while more complex, also pointed to an internal origin. The challenge for the thinkers of the time was to synthesize these disparate observations into a single, coherent theory. Famous expeditions, like those of Captain James Cook in the 18th century, included specific scientific objectives to map the Earth's magnetic field in the uncharted waters of the Southern Hemisphere. These charts were invaluable practical tools, but they were also vast datasets that fueled scientific inquiry. They revealed a global structure to the magnetic field, with lines of force that seemed to emerge from the southern part of the globe, loop around the planet, and re-enter in the north. The invisible field was slowly being made visible through the language of numbers and maps. The first great leap in understanding Earth's magnetism came in the year 1600. William Gilbert, English physician and scientist, he published his monumental work, De Magnete, Magnetisque Corporibus et de Magno Magnete Tellure, on the magnet and magnetic bodies, and on the great magnet, the Earth. Gilbert had spent nearly 2 decades conducting meticulous experiments on magnetism. He fashioned a small sphere out of lodestone, a terrella or little Earth. By moving a tiny compass around the sphere's surface, he could replicate compass behavior. Declination, inclination. His terrella experiments were a triumph of the scientific method. He noted surface irregularities caused local deviations in readings. He proposed this explained magnetic declination observed by sailors. From this evidence, Gilbert made a bold claim. The Earth is a giant magnet. That idea replaced mystical explanations with a single physical model. His work established geomagnetism as a formal science. He deduced the source was internal and his terrella captured the dipolar field. But he was not entirely correct about the source. Gilbert thought the Earth was a permanent magnet, like lodestone. He couldn't have known the core's temperatures and pressures prevent permanent magnetization. The true dynamic source remained a mystery for 3 centuries. Still, Gilbert's contribution is immense. He dismissed magnetic mountains. He dismissed celestial influences. He grounded magnetism in observation and experiment. His book framed the questions future scientists would answer. The Earth as magnet paradigm paved the way for Edmund Halley and Carl Friedrich Gauss. Following Gilbert's groundbreaking work, the scientific focus shifted from proving the Earth was a magnet to describing its field with greater accuracy and tracking its changes over time. In 1634, Henry Gellibrand made a startling discovery. He compared his own magnetic declination measurements in London with earlier records from the same location. He found the value had changed significantly over just a few decades. This was the first concrete evidence the Earth's magnetic field was not static. It was, in fact, slowly changing. Secular variation. The great magnet was not fixed, it was slowly drifting. The discovery added a new layer of complexity to the puzzle. What could cause a planetary-scale magnetic field to wander over time? Edmund Halley, of comet fame, took up the challenge. He organized the first sea voyage dedicated to scientific research, sailing the Atlantic to collect magnetic data. Based on his measurements, Halley proposed in 1692 that the Earth was made of concentric spheres, with the outer shell rotating slightly differently from an inner core. He suggested the main magnetic field originated from this inner core, and its slow drift relative to the surface could explain secular variation. Though the mechanical details were wrong, Halley's intuition of a dynamic, layered interior was prescient. The next major advance came in the 1830s with Carl Friedrich Gauss. Applying new mathematical techniques, Gauss analyzed global magnetic data. He proved over 95% of the Earth's magnetic field originated from within the planet, not from external sources in the atmosphere or space. Gauss transformed geomagnetism into a precise, quantitative science. He developed spherical harmonic analysis, a model that described the global field with unprecedented accuracy. The work of Gellibrand, Halley, and Gauss painted a picture of a magnetic field both immensely powerful and surprisingly dynamic. It was generated from within. It dominated the near-Earth environment, and it was constantly in flux. But the fundamental question remained: what engine drove it all? The idea of a permanent magnet grew untenable as knowledge of the Earth's interior advanced. Secular variation hinted at a fluid, moving source. The stage was set for the 20th century revolution in geophysics, which would finally look deep inside the planet to uncover the churning, molten heart of Gilbert's great magnet. To find the true source of Earth's magnetic field, we must leave the surface world behind. Our journey takes us on an impossible voyage deep into the planet itself. We cannot physically drill to the center of the Earth. The immense pressures and temperatures make such a feat impossible with current technology. Instead, we must rely on indirect methods to see into the depths. The most powerful tool we have for this exploration is seismology, the study of earthquakes. When an earthquake occurs, it sends shock waves, or seismic waves, vibrating through the entire planet. By measuring these waves with sensitive instruments called seismometers all over the globe, scientists can piece together a detailed picture of Earth's internal structure. These seismic waves behave differently as they pass through materials of varying density, temperature, and composition. Some waves, known as P waves, can travel through both solid and liquid materials. Other waves, called S waves, can only propagate through solids. By tracking the paths of these waves, their speeds, and the shadow zones where they don't appear, geophysicists have deduced that our planet is not a uniform ball of rock. Instead, it is composed of distinct layers, much like an onion. This seismic tomography allows us to map out the hidden architecture of our world, revealing the realms where the magnetic field is born. It is a form of planetary-scale ultrasound, giving us our first glimpse of the deep interior. Our journey begins by penetrating the thin outer layer, the crust, which is the solid ground beneath our feet. Below this lies the mantle, a vast layer of hot, dense, slowly flowing silicate rock that makes up the bulk of Earth's volume. The mantle extends down for nearly 3,000 kilometers, a region of immense heat and pressure, where solid rock can deform and flow like thick molasses over geological timescales. This slow convection within the mantle is the driving force behind plate tectonics, shaping the continents and oceans on the surface. But to find the source of the magnetic field, we must travel deeper still, past the mantle's lower boundary, to the very heart of our world. At a depth of approximately 2,900 kilometers, we reach the most dramatic transition within the planet. Here we cross the boundary into the Earth's core. This is a realm utterly alien to our surface experience. It is a world composed primarily of metal, mostly iron and nickel, under pressures more than 1,000,000 times greater than at the surface. The seismic data reveals that this core is itself divided into two distinct parts: a solid inner core and a liquid outer core. It is here, within this turbulent metallic heart, that the conditions are finally right for the generation of a global magnetic field. The journey to the center leads us to a planetary engine of unimaginable scale and power. At the very center of our planet, we find the inner core. It is a solid sphere of iron and nickel, about the size of the moon. The pressure here is absolutely staggering, over 3.5 million times the atmospheric pressure at sea level. This immense pressure is what forces the iron alloy into a solid state, despite temperatures that are estimated to be as high as the surface of the Sun, reaching over 5,000 degrees Celsius. This solid inner core grows slowly over geological time as the Earth gradually cools. Material from the liquid outer core crystallizes and freezes onto its surface. Surrounding this solid heart is the liquid outer core, the true birthplace of our magnetic field. This layer is a vast, turbulent ocean of molten iron, molten nickel, approximately 2,200 kilometers thick. The temperatures here are also incredibly high, but the pressures are slightly lower than in the inner core, allowing the metal alloy to exist in a liquid state. The key to the magnetic field lies in the properties of this specific layer. Molten iron is an excellent electrical conductor, meaning that electric currents can flow through it with ease. As we will see, it is the constant, vigorous motion within this electrically conductive fluid that generates and sustains Earth's powerful magnetic field, a process known as the Geodynamo. The existence of this liquid metal ocean deep beneath our feet is a profound realization. It means that the ground we stand on is separated from a sphere of churning, superheated liquid metal by the relatively thin layer of the mantle. This liquid outer core is not a static pool. It is in constant, chaotic motion, like a pot of water boiling on a stove, but on a planetary scale and driven by far more powerful forces. The movement is complex, with swirling eddies, powerful plumes, and vast flowing currents that move at speeds of up to several kilometers per year. This motion is far faster than the slow creep of the mantle above it, and it is this dynamic nature that makes the geodynamo possible. Understanding the distinction between the solid inner core and the liquid outer core is fundamental. The S-waves from earthquakes cannot travel through the outer core, which is how we first confirmed it was liquid. The interaction between these two layers is critical. The slow cooling and solidification of the inner core releases heat and lighter elements, helping to stir the fluid and drive the convection that powers the geodynamo. The solid inner core also helps to organize the magnetic field, influencing its overall structure and stability. The entire core system works together, a complex and interconnected machine at the center of our world. For the liquid outer core to churn and flow so vigorously, it needs a continuous source of energy. Like any engine, the geodynamo requires fuel. The primary fuel for this planetary engine is heat. The Earth's core is incredibly hot, and this heat needs to escape. As heat flows from the hotter inner regions to the cooler outer regions, it drives a process called convection. Hotter, less dense molten iron rises towards the cooler mantle boundary. As it cools, it becomes denser and sinks back down towards the hotter inner core. This continuous circulation creates massive rolling currents of liquid metal, forming the primary motion that powers the geodynamo. Where does all this immense heat come from? There are two main sources. The first is primordial heat, a relic from the formation of our planet about 4.5 billion years ago. During its violent birth, the gravitational collapse of dust and gas, and the constant bombardment by asteroids and planetesimals generated an enormous amount of heat. Much of this original heat was trapped deep within the planet's core, and it has been slowly leaking out ever since. This gradual cooling of the planet from the inside out provides a significant portion of the energy needed to keep the outer core in a molten convective state. The second, and perhaps more significant source of heat is the decay of radioactive elements. The iron-nickel alloy of the core is thought to be mixed with small amounts of radioactive isotopes such as potassium-40, uranium-238, and thorium-232. Over billions of years, these unstable elements spontaneously decay, breaking down into more stable elements. Each decay event releases a tiny burst of energy in the form of heat. When multiplied by the sheer quantity of these elements distributed throughout the core's massive volume, this radioactive decay provides a steady, long-term heat source. Another important energy source comes from the solidification of the inner core itself. As the Earth cools, the liquid iron at the boundary of the inner core crystallizes and freezes. This phase change from liquid to solid releases latent heat. Furthermore, as the iron freezes, lighter elements like oxygen, sulfur, and silicon are left behind in the liquid. This makes the remaining fluid at the base of the outer core less dense, causing it to rise. This compositional convection works alongside thermal convection, providing another powerful mechanism to stir the metallic ocean. Heat alone is not enough to generate a magnetic field. Heat drives convection, creating a chaotic, boiling motion within the outer core. But for this motion to organize into a large-scale, stable magnetic field like the one Earth possesses, another crucial ingredient is required: planetary rotation. The Earth spins on its axis once every 24 hours, and this rotation has a profound influence on the movement of the liquid iron in the outer core. This influence is known as the Coriolis effect. It is the same force that organizes weather systems into large, rotating cyclones and anticyclones. In the outer core, this force acts on the rising and sinking plumes of molten iron. Instead of just moving vertically up and down, the convective currents are twisted and sheared by the planet's spin. This causes the simple, random boiling motion to organize itself into large corkscrew-like helical columns of flowing metal, aligned roughly with the Earth's axis of rotation. This organized helical flow is the key mechanical motion that can amplify and sustain a magnetic field. Imagine these spiraling columns of conductive liquid iron as giant natural solenoids or electromagnets. As the electrically charged particles in the molten metal flow in these helical paths, they generate their own small localized magnetic fields. The rotation of the planet organizes these countless small eddies and spirals so that their individual magnetic fields tend to align and reinforce one another. What would otherwise be a chaotic and self-canceling mess of tiny magnetic fields is instead marshaled by the Coriolis force into a coherent, planet-spanning magnetic field with a distinct North Pole and South Pole. The planet's daily spin acts as the organizing principle, transforming chaotic motion into a stable global structure. This delicate interplay between heat, motion, and spin, occurring deep within our planet, is responsible for the invisible shield that protects all life on the surface. Let's delve deeper. The Coriolis effect shepherds flow within the outer core. Earth is a sphere. Rotation is fastest at the equator and decreases toward the poles, creating a shearing effect in the liquid outer core. This differential rotation stretches and twists field lines. Imagine a field line running north to south. The shearing motion grabs and wraps it around the core axis, creating a toroidal field inside the core. Diagram Part A, poloidal, toroidal. This toroidal field is a reservoir of magnetic energy, but it doesn't extend into space. Now, smaller scale helical convective columns appear. These spiraling plumes rise and twist due to the Coriolis force, and they interact with the toroidal field lines. The helical motion takes the toroidal loops and twists them, creating new poloidal loops. These look like bar magnet field lines emerging from the poles. Diagram Part B, toroidal, poloidal. This regenerates the external field. This is the two-step Geodynamo, a self-sustaining feedback loop. Poloidal, north-south, is stretched into toroidal, east-west, and then Coriolis-driven helical convection regenerates the poloidal field. The loop sustains the field as long as the motion continues. The energy comes from thermal and compositional convection, driven by heat escaping the core. How does a planetary magnetic field begin? The process requires a seed field. This initial magnetic field does not need to be large or powerful. It could be a remnant from the Sun's magnetic field captured during the formation of the solar system. As long as there is some weak magnetic field passing through the moving, electrically conductive fluid of the early outer core, the geodynamo can begin its work. This tiny seed is the catalyst for a process of immense amplification. As this conductive liquid moves, it drags the magnetic field lines along with it. This is a key principle of magnetohydrodynamics. In a highly conductive fluid, magnetic field lines are frozen into the material. They are forced to move, stretch, and twist along with the flow of the liquid. The first step in this amplification is stretching. As a plume of hot, rising iron moves through a field line, the line is stretched out, like a rubber band. Stretching a magnetic field line in this way concentrates its energy and makes it stronger. This is the first way the kinetic energy of the moving fluid is converted into magnetic energy. The countless convective motions within the core are constantly stretching and folding the seed field lines, amplifying their strength piece by piece. With a strong east-west magnetic field established and wrapped around the core, the second part of the dynamo takes center stage. Step 1. Differential rotation stretches north-south into a strong east-west field. Step 2. Helical convection twists that east-west field back into a new, amplified north-south loop. That new loop emerges from the core and reinforces the original seed field. It extends into space to form the planetary magnetic shield. The process is continuous, As long as convection and rotation continue, new north-south field lines are generated. This elegant feedback loop makes the geodynamo self-sustaining. The magnetic field generated by the geodynamo is visualized using a concept called magnetic field lines. These are imaginary lines. They map the direction and strength of the magnetic force at any point in space. On Earth, the field lines emerge from a large area around the geographic South Pole. They loop high above the planet through the magnetosphere. They re-enter the Earth around the geographic North Pole. That's why a compass needle's North Pole points north. It's attracted to a magnetic south. This overall shape is called a dipole. From far away, it resembles a simple bar magnet's field. The dipolar structure dominates Earth's magnetic field. Field lines are most densely packed near the poles. The force is strongest there. As they loop toward the equator, the lines spread farther apart. The field weakens. The angle the lines make with Earth's surface is magnetic inclination. At the magnetic poles, the lines are perpendicular, pointing straight down, or, at the opposite pole, straight up. At the magnetic equator, the lines are parallel to the surface, but the geodynamo doesn't produce a perfect dipole. Superimposed on the main field are complex multipolar components. These are smaller, weaker regional fields that deviate from the simple dipole. They arise from turbulent, messy fluid motions in the outer core. They cause magnetic declination, the angle between magnetic north and geographic north. Field lines aren't just visual tools. They represent real pathways of force and energy. They form the magnetosphere, a protective shield extending tens of thousands of kilometers into space. That shield deflects the solar wind. The Earth's magnetic field is in a perpetual state of flux, changing over a vast range of timescales. The slow, continuous drift of the field that we observe over years and decades is known as secular variation. This is the surface expression of slow, large-scale convection patterns in the liquid outer core. These changes affect all aspects of the field, including the position of the poles. The North Magnetic Dipole, in particular, has been moving at an accelerating pace in recent decades. This rapid drift requires constant updates to navigational charts and global positioning systems to ensure their accuracy for ships, airplanes, and even the navigation apps on our phones. Over geological timescales, the field undergoes much more dramatic transformations. The geological record in magnetized volcanic rocks and seafloor sediments reveals that the field has reversed polarity hundreds of times. During a magnetic reversal, the North Magnetic Pole becomes the South Magnetic Pole and vice versa. The main dipole field weakens and becomes chaotic and multipolar, then re-establishes in the opposite direction. This typically takes a few thousand years. On the shortest time scales, the field is disturbed by events from the Sun. The Sun periodically releases solar flares and coronal mass ejections. When those blasts hit Earth's magnetosphere, they can trigger a magnetic storm. These storms can last hours or days. They can overload power grids, causing blackouts. They can disrupt high-frequency radio communications and interfere with satellite operations, affecting GPS navigation and communication systems. Studying variations from secular drift to violent magnetic storms is essential to understand Earth's physics and to safeguard the technologies upon which we have come to depend. Our journey has taken us deep into the fiery heart of the Earth. Now we return to the edge of space to witness the field in action. Here the magnetosphere meets its constant adversary, the solar wind. This is a relentless stream of charged particles, mostly protons and electrons. It flows outward from the Sun at supersonic speeds, carrying with it the Sun's own magnetic field. The Earth's magnetic field stands as a barrier. As the solar wind collides with our magnetosphere, it cannot penetrate directly. It is deflected, flowing around the field. This interaction is a dynamic and often violent celestial dance. Constant pressure and gusts transfer enormous amounts of energy into the magnetic system. That energy is stored in the stretched field lines of the magnetotail, waiting to be released back towards Earth. The magnetosphere deflects most solar wind but is not impenetrable. Some energetic particles leak through the shield. Others are captured and funneled along magnetic field lines toward the poles. These lines connect the magnetotail back to the planet and guide particles toward oval-shaped zones around the north magnetic pole and the south magnetic pole. Particles are accelerated down into the upper atmosphere. As they plunge in, they collide with oxygen atoms and nitrogen atoms at altitudes of 100 to 400 kilometers. The invisible battle becomes visible to the human eye. Collisions cause the aurora borealis in the north and the aurora australis in the south. Incoming particles excite atmospheric atoms, causing them to glow. Oxygen at higher altitudes produces ethereal reds. Oxygen at lower altitudes produces vibrant green. Nitrogen contributes blue hues and deep purple hues. The auroras paint the polar skies with shimmering curtains and dancing rays. They are a living visualization of the Sun-Earth interaction and proof of our magnetic shield. The importance of this invisible shield extends far beyond the creation of beautiful auroras. For millennia, it has been an indispensable tool for human exploration. The simple compass, guided by the planet's magnetic field, allowed mariners to navigate the vast oceans, connecting continents and cultures, building the globalized world we know today. Even in our modern era of GPS and satellite technology, magnetic navigation remains a crucial backup for ships and aircraft. Geologists rely on the magnetic field, studying fossil magnetism locked in ancient rocks, to reconstruct past positions of continents, evidence for plate tectonics. Our technological civilization is deeply dependent on the stability of the magnetic field. The thousands of satellites orbiting our planet provide us with communication, weather forecasting, and global positioning. These satellites are vulnerable to the space environment. The magnetosphere shields them from the most intense solar radiation. But during powerful magnetic storms, the field can become a hazard, inducing currents that threaten satellites and power grids. Understanding and forecasting these space weather events is critical to protect modern infrastructure. Ultimately, the magnetic field is a guardian of life itself. Without it, the solar wind would strike our atmosphere directly. Over geological time, high-energy particles would strip lighter elements like hydrogen and water vapor. The planet could lose its oceans and air, becoming dry and barren, much like Mars. The magnetosphere helped Earth retain atmosphere and oceans, enabling life to emerge and flourish. As we conclude our journey, we are left with a profound sense of awe. Deep within, a turbulent ocean of molten iron churns, powered by primordial heat. This colossal engine generates an invisible force, a silent guardian that envelops our world, fends off cosmic radiation, paints the sky with light, guides our travels, and protects the very air we breathe. It is what makes Earth a living, dynamic, life-sustaining planet in the silence of space. Our magnetic field is a quiet, ever-present reminder of powerful forces that shaped our home and secure our future.